Welcome to the deep dive. Today, we're going to be exploring some pretty cutting-edge research that could, I think, totally change how we explore asteroids.
Yeah, definitely. The research paper we're looking at today is titled Autonomous Rapid Exploration in Close Proximity of an Asteroid. And it really kind of pushes back against the traditional, like, slow and steady approach to space missions.
Yeah, it sounds like this research is really all about speed. Why is that? Why is rapid exploration so important when we're talking about asteroids?
Well, think about it. If we detect an asteroid that, could be a threat, maybe on a collision course with Earth, we need to be able to act fast, right?
Mhm.
The more time we have to figure out what the asteroid is all about and then come up with a plan, the better our chances are going to be of doing something about it, like deflecting it.
Hmm.
Rapid exploration in that kind of situation would be absolutely vital.
Yeah, that makes a lot of sense. The paper mentions OSIRIS-REx as an example of, the more traditional approach to these things. Didn't OSIRIS-REx spend something like months approaching and surveying Bennu before it even went into orbit?
It did, yeah. OSIRIS-REx took around 4 months to approach Bennu, and then it spent another 20 days just trying to narrow down the uncertainty in the asteroid's mass before going into orbit. This new research is suggesting a totally different way of thinking about this. So instead of trying to get rid of every little bit of uncertainty before you even get close to the asteroid, they're arguing that we should be designing spacecraft that can kind of roll with the punches a little bit and handle that uncertainty directly.
That's a pretty big shift and think I'm curious, how do they propose to do that? What kind of technology would you even need on a spacecraft to make that rapid exploration possible?
Yeah, that's the million-dollar question, right? So the paper outlines a whole suite of sensors that would all work together to kind of give the spacecraft a real-time understanding of what's around it.
Hmm.
For example, you've got LiDAR, which is similar to the technology they use in self-driving cars, and that would be used to measure the distances to the asteroid's surface.
Hmm.
But the paper also acknowledges that those LiDAR measurements are going to have varying degrees of accuracy depending on how far away the spacecraft is from the asteroid.
So it's not just about having sensors, it's about knowing how much you can trust the data those sensors are giving you at any given moment.
Yeah.
What other sensors are they including in this toolkit for this autonomous spacecraft?
Right, so besides LiDAR, the spacecraft would be using optical cameras, kind of like the ones they used on the Hayabusa 2 mission to take pictures for navigation.
Hmm.
And, uh, and it would also have an inertial measurement unit, IMU, to very precisely track its own movement and any thruster firings. What's kind of neat is that the researchers um, decided to make some intentionally conservative assumptions about how accurate these sensors would be in their simulations. And that was to really show off how robust their approach is.
So they're basically saying even if our sensors aren't perfect, the system can still work. But how does the spacecraft actually make decisions about where to go and how to get there with all this uncertainty?
That's where the really innovative stuff comes in. The paper's focusing on two main control approaches: Monte Carlo Lambert guidance and robust path following control.
Okay, those sound a little bit complex. Can you break this down for us a little bit?
Sure. So the Monte Carlo Lambert guidance uses it's a probabilistic method for planning trajectories, and it takes uncertainties into account. So imagine the spacecraft running like hundreds of simulations to find the best way forward, kind of like testing out a bunch of different routes before picking the one that's most likely to work.
So it's not just, picking a random direction and crossing its fingers. It's really analyzing all the data it has and calculating the probabilities of success for different paths.
Exactly, yeah. And then the robust path following control system. That works hand in hand with that to keep the spacecraft on that path that it's chosen, even if there are disturbances or, unexpected events. And this is really important when you're in orbit around an asteroid because, well, those environments can be incredibly unpredictable. Yeah.
Mhm.
All of these control approaches are really designed to handle quite a bit of uncertainty. But they also kind of highlight one of the key challenges in taking this approach to exploration. And that's just that, well, a lot of times we don't really know that much about an asteroid's environment before we actually get there. For example, the estimated mass of an asteroid, that could be off by like 2,000% before a spacecraft even shows up.
Wow, 2000%. That's a pretty big margin of error. How can you even plan a safe trajectory when you've got that much uncertainty hanging over your head?
Well, that's exactly why these new control methods are so important. They're not just, passively reacting to the environment. They're constantly predicting and adjusting based on all this new data that's coming in.
So it's almost like the spacecraft is uh, it's learning as it goes, right? It's refining its understanding of the asteroid with each new measurement that it takes.
Exactly. And um and that kind of leads us to another interesting part of this paper. And that's the simulations that they ran to really test these control methods out. They decided to go with two very different asteroids as their test cases, Bennu and Eros.
Oh yeah, I remember reading about those. Bennu is that diamond-shaped one that OSIRIS-REx visited, right? And Eros is I'm not as familiar with Eros. What makes them such good test subjects?
You're right about Bennu, yeah.
Yeah.
That one was chosen because we've got so much data about it already, thanks to OSIRIS-REx,
Hmm.
so it makes for a really good benchmark for comparison. Eros, on the other hand, that's a much larger asteroid. It's more elongated, and it's got a more irregular gravity field, which makes things trickier when you're talking about navigation and control.
Hmm.
So testing their system on both of these asteroids helps prove that it can work with different, shapes, sizes, and different gravitational environments.
So it's kind of like testing a new car on a nice smooth racetrack and then, taking it off-road to see how it handles rough terrain. It's got to be able to perform under a bunch of different conditions.
Precisely.
Yeah.
Yeah, and the results from those simulations were pretty impressive. They ran 500 simulations for each asteroid, and each one had slightly different starting conditions and uncertainties. And the system was able to successfully get into those desired orbits with a really high degree of reliability.
500 simulations, that's a lot of number crunching. But even with all this talk about, fancy sensors and control systems, I still think having an accurate map of the asteroid has got to be pretty crucial for safe navigation.
Oh, absolutely, yeah. The shape of the asteroid it's a big factor when you're talking about its gravitational field.
Yeah.
And as you can imagine, even a small error in how we understand that shape could have pretty big consequences for a spacecraft that's operating close by.
So how did they account for the fact that our maps of these asteroids, they aren't perfect?
Well, they introduced a 5% uncertainty into the shape model of each asteroid for their simulations. And what they found was that even with that much uncertainty about the shape, the autonomous system was still able to do what it was supposed to do in most cases. They did note, though, that some of the trajectories got a little more erratic. So that really highlights just how important it is to keep refining that shape model as the mission goes on.
So it's not just about, having a good map before you start. It's about constantly updating that map with all the new data that the spacecraft is gathering.
Exactly. The more the spacecraft learns about the asteroid's shape, the more precisely it can get around and, the more ambitious those maneuvers can be.
This is all really fascinating. It really sounds like this approach could be a game changer for how we explore asteroids. But I'm also kind of curious about the bigger picture here. Could we use this technology for other types of space missions too?
That's a great question. And the answer is a resounding yes. While the focus of this research is on asteroids, those those same underlying principles and technologies, you could definitely apply those to a whole range of different missions. Everything from exploring the moons of Jupiter to maybe even landing on Mars.
So this is about more than just, poking around on asteroids. It's about developing a whole new framework for how we think about space exploration in general.
That's right. This research is really pushing those boundaries of what's possible with these autonomous spacecraft. And as the technology keeps getting better and better, well, I think we can expect to see even more daring and more ambitious missions in the years to come.
It's a pretty exciting time to be following space exploration. But before we get too carried away with all the possibilities, I think it's important to remember that, there are some challenges and some risks that come with relying more and more on these autonomous systems.
You're absolutely right. And I think one of the biggest challenges is making sure that these autonomous systems are reliable enough, robust enough to handle that harsh and unpredictable environment of space.
We've all seen those sci-fi movies where the robot goes rogue and, starts causing all sorts of problems. How do we make sure that doesn't happen in real life?
Well, that's where rigorous testing comes in, redundancy. You got to build these systems with multiple backups, fail-safes. So if one part breaks down, it doesn't mean the whole mission is doomed. And you also need to have those really sophisticated algorithms that can detect problems and respond to those unexpected situations.
So it's like having a plan B and maybe even a plan C built into the spacecraft's programming from the very beginning.
Exactly. And you also got to have a way to keep tabs on how the spacecraft is doing. Intervene if you need to, even if
Yeah.
it's millions of miles away.
That brings up another interesting point. How do you balance that autonomy with, the need to have some human oversight? Where do you draw the line between letting the spacecraft do its own thing and stepping in to take control?
That's a question that mission planners are really wrestling with right now.
Yeah.
And there's no easy answer. It really depends on the specific goals of the mission, the level of risk that's involved, and just how confident we are in those autonomous systems.
Sounds like there's a lot to consider, from both the technical side and just how you actually run the mission. But let's shift gears a little bit here and talk about some of the benefits of this approach. If we can make asteroid exploration faster, cheaper, more efficient, what does that mean for, our understanding of the solar system as a whole?
Well, it could be a real game changer. Imagine being able to send, dozens or even hundreds of these small autonomous spacecraft out there to explore the asteroid belt. We could collect so much data about those objects, what they're made of, their history, maybe even find signs of resources, or who knows, maybe even past life.
So instead of having just one, really expensive mission with a super specialized spacecraft, you'd have a whole fleet of these nimble little explorers out there. What kind of impact could that have on, what we know about the solar system?
It could completely change how we understand how the solar system formed and how it's changed over time.
Yeah.
We could learn about those early conditions that led to the planets forming, those processes that shaped them, the factors that might have led to life emerging here on Earth.
It's like opening a whole new chapter in the story of our solar system. But I'm also curious about the more, the practical side of things. We hear a lot about asteroid mining these days and, how those asteroids could provide us with all sorts of valuable resources. How does this new technology fit into all of that?
Autonomous exploration, that's a key piece of the puzzle if we want to make asteroid mining a reality.
Hmm.
You need those spacecraft that can identify good targets, characterize them, map their surfaces, maybe even extract samples or resources without needing humans to be involved every step of the way.
So it's not just about, sending astronauts out there with pickaxes and shovels. It's about having those robots that can do the hard work for us.
Exactly.
Uh,
And that's where things start to get really interesting. If we can crack the code on these autonomous systems, we could unlock this huge new source of resources that could benefit, all of humanity for generations to come.
it's a pretty incredible vision of the future. But before we get too carried away with these dreams of, asteroid riches, let's bring things back down to Earth for a minute. How might this technology impact our lives here at home?
Well, the progress that's being made in autonomous navigation, sensing, decision making, that's not just limited to space exploration, right? Those technologies are already starting to show up in things like self-driving cars, precision agriculture, even medical robotics.
So it's kind of like that old saying, what goes up must come down, or in this case, what goes out into space eventually finds its way back to benefit us here on Earth.
Precisely. Yeah, and that's one of the most compelling arguments for investing in space exploration. Right? It's not just about satisfying our curiosity about the universe. It's about pushing the boundaries of technology in a way that has tangible benefits for everyone.
It's a win-win. We get to explore the cosmos and we get to make life better here on Earth. But with all this talk about, the potential benefits, I think we should acknowledge that there are also some concerns, some potential downsides that we got to think about too.
You're absolutely right, and I think one of the biggest concerns is jobs. You know, the potential for job displacement as these autonomous systems get more and more sophisticated and capable.
That's a valid concern for sure. As these technologies keep getting better, we need to make sure that we're thinking about how to, retrain and reskill workers so they can be successful in this new economy.
Absolutely.
Mm.
And we also need to think about, the potential for this technology to be misused.
Yeah.
As these systems become more powerful, we need to be very intentional about making sure they're used responsibly, ethically.
But that's a crucial point. It's not enough to just build the technology. We also got to build the ethical frameworks, the regulations that are going to guide how it's used.
Exactly.
Yeah.
We need to be having these conversations now, before these technologies become so widespread that it's too late to put those safeguards in place.
Sounds like we're entering a new era of space exploration here, One that's full of potential but also comes with a lot of responsibility.
That's a great way to put it, yeah.
Yeah.
This research is really pushing those boundaries.
Yeah.
And it's up to us to make sure that we're using this technology wisely and for the benefit of everyone.
Well, I don't know about you, but this conversation has definitely given me a lot to think about. It's exciting to imagine what the future might hold for, autonomous space exploration, but it's also clear that there are a lot of complex challenges that we got to work through along the way.
I agree, yeah. This is just the beginning of a very long and very fascinating journey.
Wow, we've covered a lot of ground in this deep dive, haven't we? From like all the nitty-gritty details about these autonomous spacecraft to The bigger picture stuff, like what it means for science, for industry, even for, like the ethics of it all. I wonder if we can kind of pull it all together now and talk about what this all means for, for someone like me, someone who's really interested in space, but, not exactly a rocket scientist.
That's a great question. And I think the biggest takeaway here is that the future of space exploration, it's going to be way more accessible than it is now. We're moving toward a world where these robotic explorers are out there collecting data, testing out new technologies, maybe even, paving the way for humans to settle out there someday.
So instead of just reading about these missions in the news or, seeing a few pictures, we might actually be able to experience those missions, in real time through the eyes of these robots.
Exactly, yeah. Imagine being able to, like, take a virtual tour of an asteroid, see the data coming in as it's collected, maybe even control a little robotic avatar to go exploring on the surface. These are the kinds of things that, that autonomous exploration could make possible.
That'd be incredible. Even if we're not all going to be driving rovers around on asteroids anytime soon, it seems like, the technology behind these missions is still going to have a huge impact on our lives here on Earth.
Absolutely, yeah. The advancements in artificial intelligence, in robotics, and all those sensing technologies, all those things that are making autonomous space exploration possible, those are already rippling out into so many different industries. We're seeing it in self-driving cars, in drone delivery, in, new manufacturing techniques, even in how doctors diagnose diseases.
It's kind of wild to think that something as far out as asteroid exploration could have such a real, down to earth impact on our lives.
Yeah.
It really shows the power of, scientific research and innovation.
It really does. And,
Yeah.
and it's important to remember that, space exploration has always been this engine of technological progress. The Apollo missions, for example, those led to tons of innovations that we totally take for granted today. Things like microchips, GPS, water filtration systems, even cordless power tools came out of that.
So when we put money into space exploration, we're not just funding science, we're also investing in our own future here on Earth.
Exactly. Yeah.
Yeah.
And I think that's a really important message. Space exploration, it's not a luxury, it's an investment. It's an investment in our knowledge, in our technology, in the future of humanity as a whole.
Well said, in. As we wrap up this deep dive, I want to leave our listeners with something to think about. We've talked about how this autonomous exploration, could help us understand the universe better, how it could revolutionize different industries here on Earth. But what about the ethical side of things? What are the challenges? What are the responsibilities that come with, basically giving machines this much autonomy?
That's a huge question.
Hmm.
And it's one that we need to be thinking about really carefully. As we develop these systems and they get more and more complex, we got to make sure that they're, aligned with our values, that they're being used for good.
It's like that old saying, right? With great power comes great responsibility. We got to be aware of the potential consequences of our actions, even when those actions are being carried out by, machines that are millions of miles away.
Yeah, it's a challenge for sure, but it's also a huge opportunity.
Hmm.
By having these conversations now, while we're still in these early stages, we can help shape the future of autonomous exploration.